All right, my friends, let's finish off this chapter with the clinical applications of the sensory and the motor systems. We'll start with the sensory, we'll move a little bit to the integrative, and then we'll finish off with some of the motor problems, some of the motor pathologies. Sensory pathologies. This one, just my head. First thing I think I ever did in science, way back when I was an undergraduate, 30 plus years ago, was to do a little research paper on phantom limb pain. And my head is still reeling from it 30 something years ago. Post amputation, people complaining of at times excruciating chronic pain from the limb that was amputated. Okay? Somehow the second order ALS, because ALS for, not ALS, we'll do ALS Lou Gehrig's disease in a little bit. This is ALS in terms of the anterolateral spinal thalamic pathway that's carrying the crappy pain. But the second order neurons somehow within this spinal cord or within the lower brainstem are being pinged. Okay? They're somehow being pinged and told that you're having pain in an area that doesn't exist anymore, that was amputated off. This is just shamefully tragic for these people. I mean, is it not enough of a trauma to lose the limb? Most of the time you're losing the limb for the sake of understanding you are undergoing an unbelievable sacrifice to live, right? You're literally cutting gangrene, some sort of infection. You're literally cutting off that limb in order to survive. And now you have to deal with incredible, sometimes excruciating or chronic pain from a limb that doesn't exist anymore. And somehow that second order neuron is being pinged. Or possibly up in the primary somatosensory area. So maybe it's not in the sensation route. Maybe it's in the perception route. And you lost the limb maybe early on, and that cortical area, remember, of the sensory homunculus that was dedicated to that, hasn't received anything, and maybe you're going to start to remap, and the brain's not going to let that good real estate go to waste. So it might remap, and it might cross over a little bit. And then when you ping an area with pain that you actually, an existing body area, maybe that's kind of overlapped now in the sensory homunculus with the second order or third order neurons from areas that don't exist anymore. Make sense? Then you get a little crosstalk. So let's say your left arm's been amputated, but your right arm is fine. But in the sensory homunculus, in the primary somatic sensory area, those two areas have overlapped a little bit. So when you actually ping your right arm, you feel pain in your left arm because they're kind of overlapping in that homunculus. So anyway, just kind of mind-blowing concept of phantom limb pain. Let's talk about analgesia, and it's a big thing whenever we talk about clinical applications in the lab, or we talk anything about sort of pathologies of bone pathologies or muscle pathologies, or in 40C, any visceral pathologies. Pain killing is a huge thing, right? Aspirin and ibuprofen. You're going to know those way down here. Ibuprofen, acetaminophen, way down on the little ones, the ones that are able to just numb a little bit, right? They're blocking the formation of chemicals, prostaglandins, bradykinins, that are stimulating your nociceptor. So you're reducing the amount of stimulus. Remember, your nociceptors are chemoreceptors, ligand-gated channels that bind molecules. You're cutting down on the amount of endogenous pain signals that you're building in your own body, right? Can't do much for bee stings or the venom that are being introduced sort of externally, but you can break down and sort of slow down the amount of prostaglandins and bradykinins you produce internally, and that will eventually reduce the pain. Lidocaine and novocaine are going to be good at blocking axonal transport. So they're not going to stop the transduction, right? So aspirin and ibuprofen are actually going to stop or limit the transduction because they're going to limit the amount of binding of nociochemicals to the nocioreceptors. Novocaine and lidocaine are going to say, okay, go ahead and bind and send all these stimulus down. We're just going to shut down the axon. We're going to freeze the sodium channels so you cannot saltatory conduct this pain signal to the CNS. And that's how novocaine and lidocaine are super effective. You could be poking around, a dentist drilling through your face, and you don't feel anything other than a weird numbness because those signals aren't getting through. All right, and then go way up the top. Fentanyl, carfentanil, just keep going. Gray death. Things where a small bag is punctured into the air and everybody in the room dies kind of thing, right? And so they don't care at all. Opiates and opioids, what's the difference? Opiate is the natural chemical, morphine. from poppies. An opioid is a chemically laboratory synthesized derivative where they can just keep making them stronger and stronger and stronger and stronger, i.e. fentanyl, carfentanil, gray death, right? There's no telling how strong they can get, really. And they don't care. They allow stimulation, they allow transduction, they allow sensation. It's just when you get all the way up to the top, they're just going to change perception. So, I mean, these things are ringing. Screaming agony is ringing through your body up to the cortex, but the opioids and the opiates have rearranged your cortex to the point where you just don't even care, or you're just blotting them entirely out at the cortical area. So they're not perceived, right? And go back if you want, watch that video on somatic sensations between stimulus, transduction, sensation, and perception. And know that opiates and opioids work at the highest level of perception, where they're just modifying how you perceive that sensation. All right, staying with sensation in the dorsal columns. Syphilis, sexually transmitted bacterial disease. Some of the lesions on the face are grotesque. I'm not here to talk about that. I'm talking about late tertiary stage progression of syphilis. Somehow the bacteria gets into the dorsal columns. Picture your spinal cord, your anterior gray horn, your posterior gray horn, or your posterior column. Sorry, not your posterior gray horn. Your posterior white columns. I love this image, just on fire, just being destroyed. What was there? Do you remember? Gracile fasciculus and cuneate fasciculus. This is your DCML right here, being absolutely shredded by the bacteria of syphilis. If your DCML is being shredded, you're not feeling light pressure, you're not feeling light touch, you're not feeling vibration, you're not getting proprioception. You're not able to get proprioception up to the cerebellum or even to the cortex. You're not able to figure out where you are in space. Your movements become uncoordinated, jerky, loss of balance, and you're just losing all that proprioceptive information, right? Let's move a little bit more into the integrating. Before we jump to motor, let's move into more of the integrating. Let's move from bacteria to virus. You guys must all know West Nile virus, sort of a lingering threat around our world out in California. So, injected by the mosquito, it's a virus. Only a very small, less than 1% of the infections target the nervous system. But when they do, they are devastating when they get in the nervous system. Why? Because they cause inflammatory lesions. Remember, a lesion is some kind of pathological damage or destruction to the brainstem. Well, that'd be kind of important, wouldn't it? To the thalamus, to the cerebellum, and to the cerebral cortex. And obviously, hopefully, you can get the devastation on the integrative side, where all the sensory information may be able to come up, but all these relay stations in integrative areas, cerebellum, thalamus, are unable to relay properly, and that's why West Nile virus, once it gets into your nervous system, can be absolutely just extraordinarily pathological. Fortunately, it doesn't often get into the nervous system, but when it does, you want to beware. All right, motor. Onto the motor side. Lesions of upper motor neurons and lower motor neurons, right? And if you're going to have lesions and you're going to demyelinate all of the lower motor neurons, all of them, leading to your skeletal muscles, you will be talking about polio. And if you're old enough, not me, but if you're in your 80s and this whole COVID thing, it's your second rodeo. COVID thing is your second rodeo. Your first rodeo, I mean, if you were 120 years, 110 years old, your real first rodeo would have been the Spanish influenza of 1920 or so. And that would have been some kind of rodeo. And then your second one would have been the polio epidemic. And now your third one would be COVID. But if you're about 80 or so, your first rodeo was the polio infection and the polio virus. And it gets into the lower motor neurons and it demyelinates. So you lose conductive ability. You lose coordination of the alpha motor neurons going to all your skeletal muscles. And you just sort of debilitate all your skeletal muscles. At the bottom is Franklin Delano Roosevelt. I believe that's in his Warm Springs retreat in Georgia. He was elected president in 1936. He was elected president in 1940. Oh, back up. He was elected president in 1932. He was elected president in 1936. He was elected president in 1940. And he was elected president in 1944. Thus, the rule that you can only be president for 2 terms because he was president for 13 years. He would have been president for 16 years, but he died in 1945 of the effects of polio, and that's him in a wheelchair. Many people say, historians, that if any, this is 1936, 1940, early 40s when he got infected, before television. He gave these radio fireside chats. One of the most charismatic. Obviously, the guy was elected 4 times. Mount Rushmore was built in, I think, the early 1940s. He's not on the next Mount Rushmore. He will be numero uno on the next Mount Rushmore, or whatever monument celebrates from the great presidents of the 1940s onward. He will be numero uno. But most people think he never would have been elected if anybody knew, and nobody knew, that he was in a wheelchair from polio. Other celebrities, Neil Young comes to mind right away, was a polio victim. So in this case, some of the polio pathologies are really hard to find, and people were fortunate. Mild infections, they might have had some sort of aberration or slight loss of motor function, but they might have been able to recover it. Where's the problem? When you get to the diaphragm, when you lose skeletal control, muscle control of the diaphragm. These are iron lungs, each one of these things. That's a child. That's a child. This is a child. You want to talk about the holy terror of being a parent? This is a child. That's a child's head. That's a child's head. That's a child's head. These are iron lungs in the early 1950s. These are children being put in an iron lung to save their life because they can no longer breathe, right? The polio virus infecting rampantly, screaming through the population, targeting children. Can you imagine the panic if COVID was just killing children by the thousands upon tens of hundreds of thousands? That's what's happening, and that was what was happening in early 1950s in this country. And anyone with any money was headed to the hills and isolating, and literally just leaving congested areas and spending months upon years in the hills, in the mountains, getting away from every other human being until this epidemic passed. How did it pass? You guys know this. COVID, vaccination. Jonas Salk. Look up Jonas Salk and the polio vaccine, right? He is called the miracle worker for a reason. Getting that vaccine into children's arms, getting needles in arms, and effectively, for all intents and purposes, what we hope with COVID, just wiping polio off the face of the earth for the most part, right? For the most part. All right, and speaking of lower motor neuron, so upper and motor undergoing irreversible sclerosis. What is sclerosis? Hardening. Arthrosclerosis is hardening of the arteries, right? This is lateral sclerosis. It's hardening of the myelin sheath. So they're not being degraded as in loss of myelin, but they are hardening, and it is very slowly just kind of choking out your neurons because there has to be some fluidity in the myelin sheath. It's just phospholipid membrane. There has to be some fluidity there to allow saltatory conduction and proper alpha motor movement through the upper and the lower motor neurons. And sclerosis is just generally weakening that conductive, and you're just slowly losing control of all of your skeletal muscles. Amyotrophic lateral sclerosis, ALS, it is known, of course, as Lou Gehrig's disease. That's Lou Gehrig's. That's Lou Gehrig right there. Look up I'm not a huge baseball fan, but any list of the greatest first baseman to ever play baseball in the last 150 years has one name on it, and that name is Lou Gehrig. Right? This is him on July 4th in 1939 at Yankee Stadium with 70,000 people in the crowd, and he is 2 weeks from his diagnosis of ALS. 2 weeks from being told you have a fatal, degenerative, unstoppable, irreversible, incurable, horrifying muscular disease. And any baseball player, any baseball historian will tell you the speech word for word by heart. They say 70,000 people in the stadium. There were 140,000 crying eyes. And this is what he said. For the past 2 weeks, you've been reading about the bad break I get, yet he stands there knowing he's dying, and he tells the entire world that he feels he's the luckiest man on the earth. I don't even know what to say about that. He was dead. It's 20 months after this, from playing 2,130 consecutive baseball games, and being the most fit and the greatest first baseman to ever play the game, to being dead 20 months later. Okay, it's called Lou Gehrig's disease, ALS. They're starting to make some strides on it, hopefully, starting to really maybe kind of understand and come up with some ways to stop the sclerosis or the sclerotic effects on the myelin sheaths. Okay, and then MS we have done previously back with the axonal transport. We know that we're demyelinating the axons on upper motor and lower. So like polio, we're losing control slowly of multiple sclerosis. We can go into remission on multiple sclerosis, hopefully, we can slow it down and get some hope here. But I want to introduce the concept of pleiotropy here. And what is pleiotropy? It's an important thing you should know. When we get into 40C and genetics a little bit, slight genetics, you'll want to know that pleiotropy is a series, a long range, and I love this visual going around the horn, but a wide range of phenotypical, these are all phenotypes, right? Or phenotypical conditions, physical conditions. A wide range of phenotypical pathologies all generate from one genotypical pathology or one genotypic mutation, right? That's causing this demyelination. And it's important to know things like polygenic, or when you have a whole bunch of genotypes that only affect one phenotype. But you should also know pleiotropy is when you have one altered genotype, so one mutation in one gene, in one protein, but it just leads to a massive number of different phenotypes from MS. And all these are symptoms or pleiotropic pathologies or phenotypic pathologies of multiple sclerosis. And so this is just an important thing to know, that one bad gene or one mutated gene can really lead to a ton of phenotypic pathologies or symptoms. And then we have coach basal nuclei and what happens when you go wrong with coach basal nuclei. I'll draw it just for the sake of drawing it. You're coming down through the internal capsule to the putamen. You're running from the putamen to the caudate nucleus, then to the putamen that I'm highlighting now, then to the globus pallidus, back to the thalamus, and back to the premotor area. Unless you have Huntington's disease. And if you have Huntington's disease, you are slowly degrading and destroying the caudate nucleus and the putamen. And that is horrific. Horrific. And Huntington's disease is an dominant disease. What does that mean? It means this is Jake Dowell in the white shirt, a multimillionaire National Hockey League hockey player of the epic proportion, who is watching his father die of Huntington's disease in the wheelchair. You can see in the wheelchair, yeah, he's in a wheelchair. He was dead very shortly after this photo. Watching your father die a horrific disease where all motor coordination is lost because, not all motor coordination, but all the edited plans. Remember, this is the editing loop, right? You can no longer edit the loop whatsoever. You are at the whim of really bad motor plans and just degenerative motor plans until you essentially degenerate to complete loss of motor function. It starts at about 35, sometimes maybe 45. Short length, and there is no surviving it, and there's no lasting more than, I think his father John Dow here lived to be almost 55, I think 56 or 57, which is way out there, way up there in the life expectancy. But it's a dominant disease, so look up the Jake Dowell story. It has the exact same title as every other person in his position. It's called, every film, every documentary has the exact same title. The Jake Dowell story, replace the name of somebody whose father had Huntington's disease, flip of a coin. Meaning 50% he's going to die of a horrifying disease, and 50% chance he's not going to die of a horrifying disease. In his case, he got lucky. He drew the right side of the coin. He does not have Huntington's, but he has a brother. This is Luke Dowell. 50% chance. Luke Dowell died not long after this at, I think, 35 or something like that of Huntington's disease. Just his entire life stripped from him. So as if it's not bad enough watching your father die in horrifying agony, you then watch your brother die in horrifying agony. Okay, and that's all because of the breakdown of the caudate nucleus and the putamen, and that ability to edit any motor plan and just general loss of degeneration of your basal nuclei. Okay, and as if that's not cheering enough, what is the other route? You're coming out of the primary motor cortex. You're coming down to the caudate nucleus. You're coming to the putamen, and then to the globus pallidus. But remember, from there, you can also cruise the substantia nigra, right? And you can also run down from here to the substantia nigra, check in there, because that's part of the basal nuclei, then back to the thalamus, and then up to the premotor area. Unless you start breaking and you start having lesions in these neurons, and you can no longer make that check with substantia nigra. What happens then? Well, you start to lose the ability to initiate movements correctly. You start to lose the ability to get rid of unwanted movement, like shaking, okay? You can't initiate movement, so it's stunted and staggered. Any of this sound familiar from Parkinson's disease? right? Again, completely adding in unwanted movement, really stultified or kind of stunted movement, and then loss of movement and hypokinesia, decreased range of physical movement, rigidity, and all that shaking from Parkinson's disease, from breaking, ruining these neurons that are running down to the substantia nigra. Okay, that's it. That's all I got for you. Thanks for watching this, and thanks for finishing out through this tough chapter. And let's head into chapter 17, and let's start to look at the eyes and the ears, special senses, and enjoy kind of learning about how the special senses are transduced into your brain and how you see, how you hear, how you smell, how you taste, and how you maintain your equilibrium. All right, thank you very much, and I hope you got something out of this.